Okay, pretty good. So we can break this down, and I'll go on to my notability page. Okay, so let's just do a little bit of review on galvanic cells, so we're all on the same page here. But you guys seem to know, you guys seem to understand. So just to review, the anode side is always going to undergo oxidation, and that means whatever is in solution here. Let's do using our half reactions here. We're going to say the zinc is going to be the anode since it has the lower SOP here, and this zinc 2 plus is turning into zinc. It's being this zinc solid is turning into zinc 2 plus. It's being oxidized. That means we're going to be losing some mass here, right? Because that mass is turning into the aqueous form with less electrons here. And we have that salt bridge. We have our anions traveling this way, our cations traveling this way, and not electrons going through there. They go through here. So then we reach the cathode side. I just put platinum there just so you guys can recall. Platinum does not affect the cathode, does not affect the cell potential if it's on the cathode side. So it's all good there. And we could put our gold 3 plus in solution, and that will be becoming reduced. So it'll be turning into solid and it'll kind of accumulate here. And kind of that's what's conceptually going on. If we were to calculate the cell potential, we would take the difference between these and we expect a positive number. So the difference between these, let me calculate that. 1.5 plus 0.76. 2.26, okay? And whether this is spontaneous or not is also important. So this is a spontaneous reaction, and it will have a negative delta G. Okay. So those are kind of like important characteristics of galvanic cells that we've already looked at before. Okay, any questions here before I go to the next question? Okay. Okay, so now we're going to be asking about concentration cells. What does the standard potentials look like of the cell? Is it spontaneous? Is it non-spontaneous? What drives this cell? Is it that concentration driving to equilibrium? And then in concentration cells, we have the same half reaction. And my question is, which one is in the reactant side? Because they're going to be the same ion, let's say K plus potassium, is it going to be, which one's going to be in the reactant, which one's going to be the product, if they look the same? Okay, I'm going to continue now. Okay, so we can break this down, but you guys got the majority right. So if we're looking at concentration cells, I put this example here with potassium, we have the same half reaction happening. And the only difference between these ions here is their concentration, and that's what drives the reaction, is their desire to reach equilibrium. This concentration gradient is powerful to drive equilibrium and create some energy. So I have set up here the K plus and K plus there. And what I want to emphasize is which one should be in the reactants, which one should be in the products, because this will help you calculate Q, which you will use for questions that you deal with. And so it's important for you to recognize what goes into Q. And then you need to, the key part is to recognize which product and reactant. So the logic here is that if we're trying to reach equilibrium, we want to start with the higher concentration and give that concentration, those ions, to the lower concentration area. You know what I mean? We want to drive, there's a lot of, it's very concentrated here. It's very concentrated K plus, and we want to drive that toward equilibrium. So hopefully that makes sense, where the reasoning behind which one should be in the products, which one should be in the reactants. Another thing to talk about here, and this is really important also for calculating, is what the standard cell potential is. In this case, the standard cell potential should always be calculated with the difference, right? The difference between half reactions. And here I don't see any difference. Don't worry about adding or subtracting. Don't get too confused. The answer is 0 here. Okay, so that is the standard cell potential, and that's a characteristic of all concentration cells that you really should remember. But you can also see that there's no difference in this. Therefore, the only way that this can be run, this cell can be run, is through that difference in concentration, and then that leads to the question: is this spontaneous or not? And the answer is yes, it is spontaneous. It's trying to reach equilibrium, and so it is spontaneous. So you're going to have, again, negative delta G. Spontaneous. So any questions on concentration cells? I want to make sure I hit every point here. Yes. Okay. My next question is about electrolytic cells. So the first one, what's going on with the anode and cathode? Is it different? Is it the same as galvanic cells? Similarly, the second one is asking what's happening to the anode, and that's related to the first statement. The third statement is asking if it's spontaneous or not, and the fourth one is asking about platinum, and if platinum has a different role here, and if it can affect the concentration, or if it can affect the electrolytic cell differently. Okay, I'm going to go forward. Okay, not bad, pretty good. So in electrolytic cells, the anode will still be oxidized, the cathode will still be reduced. That is really characteristic of all cells, and that's something that does not change. The only thing that changes is really which one can we call the anode here, and which one can we call the cathode. Which one are we going to put in the cathode or in the anode or cathode? In the first in the first half reaction here, it has a lower SRP. Traditionally, for galvanic cells, we would call that the anode, right away. But it's opposite here. So this time it'd be the cathode. This would be the anode. And that's really the only difference. That difference, though, is important because it has consequences for delta G, if it's spontaneous or not. And energy needs to be input into the system here, into the cell, for it to go forward. That means it's not going to be spontaneous, okay? So it's going to have positive delta G, and it's going to be non-spontaneous. Okay, so why am I like not spelling spontaneous correctly here? Let me non-spontaneous. Okay. So this time we would label this one as the gold here. And zinc on this side. Okay. What other differences? Oh, yes, about the cathode and the platinum. So if we had a platinum put in place here instead of the zinc, that would similarly not affect the cell potential, right? Because the cathode and the anode still have the same rules. They still, in the anode, oxidation occurs, the cathode reduction occurs. That doesn't change. And so having platinum on the cathode side is not a problem again, okay? All right. And similarly, the anode is not gaining mass. It will be losing mass because it is going under oxidation. So, okay. Any questions before I move on? Oh, that's actually a good reminder in my email. The CLC is not open tomorrow, by the way, if you were looking for office hours, but I'll still be answering emails. No problem. Okay, so the next question is about standard cell potential in an electrolytic cell. Here are, you have zinc and gold, the half reactions I just put out, and those are the two SOPs there. So it's negative 0.76 and 1.5. Just need to find the standard cell potential. Okay. Okay, good. So yes, it should be, number one, it should be negative. And number two, again, it's the difference between them, but this time it's like the negative difference. So the concentration at the anode still increases. Yes, because it's being oxidized. For example, if we have the gold here, the concentration would be increasing since the gold is turning into its aqueous form. Okay, now a little bit about kinetics. What do molecules need to react together? What are important important things that molecules need to react? This is related to collision theory. Okay. So yeah, it's actually all of them. Yeah. So they need the right orientation that they collide in. It needs the proper energy, and you need the right molecule. Not just any molecules are going to react with each other. They need to have the right properties, right structure. Um, Otherwise, everything would be reacting all the time, and we definitely don't want that. So another question is, what affects the rate constant K? Okay. Okay, I understand. I understand where this is. This is really important to address. Okay, let's break this down. So pressure. Well, I'll actually go to my slide here. So pressure has nothing to do with anything. We don't see pressure anywhere. We don't deal with pressure. However, we deal with activation energy and temperature. So the Arrhenius equation, and this is really a beautiful equation. It shows you everything that affects K, okay? And there's only two things, and it's the activation energy and the temperature, okay? You might think concentration, and I understand why you think concentration, because there's equations that involve K with concentration. And it's tricky, but K is not influenced by the concentration. It does play a role in the rate laws and things like that, but it doesn't change because of concentration. It's not dependent on concentration. It's only dependent on the activation energy and temperature. That's why we'll need to calculate new Ks. And I don't know if you've learned that yet, but it won't be on this exam or on this quiz. But if we have different temperatures, we need to calculate different Ks, different rate constants. Okay, any questions on that one? Okay. So this last question here is about units. Um, so I don't think like you'll have to ever write out the units, sorry. But it's important to know kind of what the units are for different ordered reactions. This one is asking about first order reaction. What would the rate, what are the units of the rate? Okay. Are you ready to see the answer? Um, it's 1/2 seconds. So here are all of, I wouldn't say necessarily memorize this, but at least be familiar. For zero order, it's going to be the molarity over seconds. First order, it'd be 1/seconds. So as you notice, what's happening here, the molarity is decreasing. So in the first order, it's going to be 0 power, but the power is decreasing. So here it's 1 power, here it's like the 0 power. Then we have -1 and then -2. We haven't talked about third order reactions, but at the same time we have. A third order reaction can just be like rate equals K. This is third order, for example.